Hey, what's up YouTube? How's it going today? So here we are back again for some more Optimal Start Math Playground. So like we've been talking about a lot before, this is mechanical engineering theory. We're studying the math models that can optimally start an HVAC system before the building is occupied. These models predict minutes to recover the zone, either warming them up or cool them down. When you feed in zone temp information, set point, occupied zone set point data, and scheduling information from the building automation system. Once again, these models are like firmware that would be running in the building automation system, and they wouldn't be necessarily something the building automation technician is coding or setting up when a building is set up, but more or less something the manufacturer would supply, if they even have it. Some building automation systems don't even carry optimal start models, and if they do, they're very primitive. So all of this is coming from the research paper in the PNNL directory. That's this. I highly recommend to read over the research paper, resistive capacitance type models. And we've studied all these models before: Model 1, Model 2, Model 3, the quadratic, or the multiple linear regression, and Model 4, which is the simple first order response model. So we're doing this in Python in our AI generated coursework. And I created 2 more weeks of bonus day materials to study this more in depth, on the multiple linear regression, how to do this without some math libraries, which was getting into the weeds of matrix algebra, and even this first order model as well. So now we're back onto the normal lesson. Not or I have come on words. We're back onto the normal lesson plan after the bonus days. So we did all of our bonus days, and now we can jump back to day 30, which we actually did. That's where we left off. So we were talking about Model 4. Model 4 uses the log math equation. So this was, I should go back into the paper, but the paper calls for to do, I think this was alpha A is the deadband, alpha B parameter was the delta temperature, which is the difference between zone temp and the occupied zone temp set point, and then the decay rate, or alpha C. I think that's the parameter that we were computing, the high iterative approach. Oh yeah, it says right here. So the decay rate, alpha C. So where should we actually did this before. So this way, we went deep into the weeds before on how they come up with this decay rate. And then this is pretty much the nuts and bolts of Model 4. But this was like the complicated part. If you remember, this was our Python script in estimating C, the least squares regression form. So it's an iterative way of estimating the decay rate. And then ultimately we take the where is it here? Where's this? Oh yeah, we take our log. There's our log math in our Python script. So yeah, we actually did this. So maybe I'll just jump to day 31. Now we're a little smarter after our, at least I am, after our bonus day material. So let's get back into it. We still have 20 more days of material. And then some of these last couple days are, I thought it would be kind of cool. to play around with some concept ideas of hybrid models going beyond this research paper, because artificial intelligence has some ideas on how to do that. So let's play around with it. Here we go. So day 31, calculating decay rate, which we've done a lot already. Model 4 requires decay rate, alpha C parameter between 0 and 1. One way to estimate it is to examine the error, zone temp set point minus the zone temp, changes minute over minute. So that's like we talked about this before in our script. This was confusing to me, but this is actually an array of data. So like the zone temp is getting closer to set point. So we would be sampling the data every minute and kind of watching it get closer and closer to set point. So if the air temperature and the whatever this is our consecutive errors, the ratio approximates C. Averaging these ratios over warm-up time gives a good estimate. So I think they're saying you'd be averaging, this data, this data, this data, this data. You plow through it, plow through the array in this math right here. Averaging these ratios over warm-up time gives a good estimate. Apply the concepts above using the formula or algorithm provided, refer to the minis. So here we go. So, well, let's just run this. This might be too easy now that we've done a full-blown Model 4 by hand, but for me, I'm actually kind of glad we're doing this because I thought just understanding this was a little harder for me. I thought the linear regression Model 3 by hand was really hard, but this one is maybe a little bit easier, I think. No matrix algebra. Okay, so record delta temperature every minute during warm-up time and compute C. We did that already. So that's what it's doing. It's this. Okay, so some of these are kind of redundant lessons, I think. So I actually recorded that code that we made the last couple days for Model 4. I've saved it here in a separate file. So I think that this there's like a little iterative for looping process that's right in line, called a list iteration, I think. I think that would be the same thing as all this code here. I like the way this looks a lot better. This is easier for me to understand than having it in this format, but so basically they're summing this data, and that's the length. We could even print these two values just to see. Print. Could even just do this instead of the division, just to see what these numbers look like. Whoops. So the sum of the ratios, maybe we should even print ratios. See what that looks like. So it does. So this is our original delta temperature during our warm up or cool down, and it does kind of I guess this is this would be C, the decay, the alpha C parameter, and this is the sum and length. So the average would be 0.78 is the decay, this decay ratio, unitless number. What does a C value approximate to 1 imply about the system? Okay, so we were asked this question a little bit earlier, and I think that part of the clamping, that it should never be above 1. Because I think that so like how this is, let me think about this. So 1 minus 0.78, that would be 0.22. So I think that it approximately tells you that like when the zone is warming up, like each one of these minutes is approximately 22% difference on average. I think that's what that means. So if it's closer to 1, then there wouldn't be any warming up or cooling at all. I think we could even simulate that. So we could do 7.9. Let's just put in a value of, so this would be simulating that our sensor our zone is not warming up at all, only a 1/10 of a degree. Like the HVAC system is broken, so that it's 1. Yeah, so that's what would happen. Our HVAC system it's broken. It's not doing anything. It's not warming up or it's not cooling. Why must alpha C be less than 1? So that's just indicating that something's happening to the zone. Like we were talking about, it's a percentage that our decay rate acts as a percentage. Create a simple Python file that performs a calculation of this lesson. So, I'm feeling too lazy to do that. I think this would be kind of neat to try this by hand, debating about whether it should do that or not. Might be good practice. I should give myself like a 5-minute timer. If I can't turn this, I should just turn, let's just try it. We could just make this into a function in Python called ratio maker, and we would pass in, this would be our data as a list. Whoops. I could just cheat. Actually, we might do a lot of cheating. So we could just say, this should just be, I would just have to change this to this and to that name. And you could just say return. So then I could just say ratio equals ratio maker, pass in our errors. Whoops. So this is just computing the same thing. And I forgot a colon here. Okay, so it would be a fun exercise. I mean, this is more professional looking, I guess. But just for the fun of it, do a little Python programming. I'm just trying to think how you would do this in a for loop fashion. Like I want to do something that would be like, looks like this. Let me see. So this is just computing the ratio. I think could just do okay. So we could try. Sorry, I'm trying not to cheat, but I'm kind of cheating. So we could do for, let's just copy this. For I in range, length data. No, let me see it. What is this? So this returns a new list. I could say new list. Okay, so we could say new list dot append our math, and then say return new list. I wonder if we get the same results. Will this work? Oh, and it works. Did it work? Okay, we got same. So I don't know. Sometimes this is better way to write it. I think it's a more, this is probably what AI would create, which it did because it created this lesson plan for us. But this is something that maybe a very advanced Python programmer would do. For me, I'm just not that advanced. And I think it's kind of fun to challenge yourself. Maybe someday it would be fun to get a computer science degree. This is kind of more like computer science 101 algorithms or something. I love doing this kind of stuff. So, all right. So I think we satisfied our little Python file, for this lesson. So maybe that is enough for one day. So thank you for joining me today, and tomorrow we will be on to day 32 out of 50. So we're getting close, little by little. Have a good afternoon.